Are you good with recording this lectures?
Yeah, that's fine.
And then the next question is, what about posting? Is it necessary that we post it privately, or can I just post it publicly? Publicly means the whole world looks at it. And not that anyone cares, but no one will enter into this. But in principle, it's available. That's the thing. So you feel comfortable about that? Otherwise, you just do it privately.
It doesn't matter to me.
Doesn't matter to you. Okay. Yeah. Angela, your vote remains the same as earlier.
Yeah, I'm fine with anything.
Yeah, it's just convenient for me to make it public. Otherwise, I would go and give permission each time to everyone. And but if there is any concern, I would prefer. I don't mind making it. Okay. Just, let me know. For undergraduate classes, I've decided to make it private in case because it's a bigger class, also slightly bigger class. Okay. So, what are the things? You just remember where we were as far as homework goes. I think homework 6 was not made due, correct?
Correct.
Homework 5 was already. You guys have already submitted it.
I haven't submitted it.
You have it. I have a couple of few homeworks. I think 3 homeworks on my desk in the office, which I did not bring with me. So I don't know which one to do. But not up to date as far as grading goes. So as of now, there are no homeworks due for this course, and whatever we are going to do basically is in the form of a homework, but I'm going to do it in the class. So probably today and Thursday we will have homework. I'm not sure. Yeah, I think today I won't post any homework, but I think probably Thursday I will post the homework. So that's all. Okay. So no homework as of now. So is readable? Yeah, I have to zoom in and see this, right? Justin, how is it?
Good.
Can you read what I wrote there?
Oh, yes.
Yes?
Yeah.
Okay. So should I be zooming in, Angela?
I think it's fine for now.
Or not?
Yeah, it's fine. If it needs to be zoomed in, I can tell you that.
Okay.
Right? Yeah.
So homework 6, that is, it has been posted, but this is not due. Yeah, not due. And yeah, the bigger question is the midterm, which is supposed to be Thursday. I suggest that we don't have the midterm on Thursday. Instead, postpone it by 2 weeks. What do you guys say? Justin?
Yeah, good with it.
Justin?
Oh, yeah, I'm fine with that. You can just do away with it if you want. Yeah, we don't need to have it. Know that.
It would have been okay, but we have this student, one more student among us, who is never there, so I had to grade him. So yeah, so I have to have the exam. So otherwise, I will not have any paper trail on it. Right, so I have to. So we will have it, but just as you shall probably take home exam, it won't be a classroom exam, pretty much like last time. But it's postponed by 2 weeks, so that makes it, when does it put you into stuff like 15 possibly?
Side note, I kind of feel like your audio was better in the morning session than now. I don't know if something has changed in my setup or is it yours. Kind of feel like the audio was better. I mean, I can still understand what you're saying, but
Okay, audio is Disturbing.
A little
Okay.
reverberation sort of thing. Is like it's not.
Okay. What could it be? In the morning it was different, so it was exactly the same. Okay. The suggestion is that it might be the load on Zoom. And now, Angela, you are frozen.
Yeah, it's frozen on mine too.
Yeah.
Okay, now you're unfrozen.
Yeah, now you're.
Oh, I think maybe it's my internet that's bad.
Yeah, I think you froze for a moment there.
I think it's probably my internet. Okay, never mind. Go on, go on.
So, is it manageable?
I'll see how it goes. Yeah.
Okay. So, this is going to get recorded, so that's where this recording really will be helpful as it is.
Mm-hmm.
That I don't make a mistake in recording and all that. It's up to you. Okay, I was saying that midterm 2, we can have it 2 weeks down the line from Thursday. So that will be what, 26, and we add 15 to it, right? What's the date? Yes. 26.
I believe it's April 9th, I think. I looked on the calendar, I think it's April 9th.
Huh?
I looked on the calendar, I think it's April 9th. 2 Thursdays, Thursday.
Next Thursday?
Thursday?
No, I think April 16th, for 2 weeks from now, right? Oh, you want it next Thursday?
It'd be 2 weeks from this Thursday, should be April 9th.
Yes.
Yeah.
Did I say it wrong in the morning? Yeah,
I think you said April 14th in the morning.
Yeah, I think that was wrong.
Maybe you meant April, like.
Yeah, I think I made it 3 weeks there.
Yeah.
Right? Is that okay? April 9th, or we can push it one more week if you want. We make it April 16th, then we have only 2 weeks remaining after that. I think 2 weeks this is good enough. What do you
I
guys
think
think?
that's fine. Like, I think it'd be better if it's not too close to the final. Like, you know.
Exactly. Yeah. So I think in 2 weeks we should get used to this new system reasonably well, I guess. So let me write that down. Okay. And the final exam, assuming everything goes well, is on May 6th. But I'm not going to write that. Okay. So even though the bandwidth is low, Angela, you can read this one, right? That's what.
Yeah.
Okay. So we were doing kinematics, like relativistic kinematics. And we barely started on this last time. We introduced the 4 vector, I suppose. So let's repeat that process a little bit just so that we know where we stand. Like we do in the standard elementary physics, we start with time and position. So we introduce what we call the 4 vector, so let's say 4 position. So instead of talking about the normal space and time, we put them together and say this is x mu. But x mu is where mu goes from 0, 1, 2, 3, and this is equal to x0, and vector. That's clear. So that's so x0 we will mean time, right? And just to make the dimensions correct, we will in fact say this is c times t and the position x. That will be our notation. It's necessary that mu is on top. We will have a symbolic notation for what is mu on top and what is mu on bottom. Okay, so that's going to be the definition of for position. While we are there, what is x mu? Mu downstairs or contravariant vector, and that will be minus the t. So notice that it is only the time component that changes sign. The spatial part remains the same. Okay. Okay. So that's going to be the definition of for position. So when we are doing elementary physics, we first define time, then position, and then comes the definitions. We define velocity as rate of change of position with respect to time, and acceleration as rate of change of velocity with respect to time. And here we want to do the same. First, we have position, which has both time and space in it, and now we want to define what is for velocity. For velocity. And we will call it u alpha. So, or x, this could have been x alpha. Right? Usually, I think that's a good point to point out, like all the Greek letters, alpha, beta, gamma, and so on, whenever that's there, it's considered to be running from 0, 1, 2, 3. So that's it. It's not necessary that you really obey this, but general convention is that whenever you use Greek letters, that represents all the 4 coordinates. And if you use Latin letters, for example, I, J, K, and so on, they run only from 1 to 3. So that's the standard spatial context. And for velocity, we will define as u alpha. That means there is u of 0, and there is the spatial vector u. That's u1, 2, 3. So that's the 4 quantities, and we are going to define this as, this will be defined to be the x alpha, like whatever is your for position with respect to the proper time ds. Now, what is ds? Let me switch to the other board. Readable, right? All these are readable. Okay. So what is ds there? So remember our metric was s square is equal to minus c square d square plus x. So that's your metric. If you want, you can write this as dx1 square plus dx2 square plus dx3 square. And here we are taking a derivative with the proper time ds, not the usual time. So this is the physical time that an observer will measure. T, that's the standard time, and this is the standard position. That's what we use all the time. But now we have a new quantity. That's this is usually called proper time. So S is called the proper time. And what is the significance of that? Remember, we pointed out that if you have a rotation transformation, it is not the components that's important. What remains the same for every observer is the length of the vector. So in that sense, the proper time is an invariant quantity. Invariant in the sense, whoever measures this, if you measure the proper time, it will be observer independent as far as Lorentz transform goes. So in that sense, this is more convenient object when it comes to different observer. Nothing wrong with measuring normal time of position. It's just that then you have to make the transformations to get it right. And we pointed out last time that this tells us that I can take this common out, and I have 1 minus dx by dt comes in. So this will be velocity. So that's velocity over c squared. And so we define beta to be velocity over c, and gamma to be 1 over 1 minus beta squared. Right. So that's 1 minus beta square showing up. So there's a gamma square in the denominator. So this tells us that the square is minus c squared equals square over gamma. Or gamma square. We can take the square root of this, and our usual understanding will be that if I were to state this, this will be gamma will be equal to c times dt over ds. Or you can write c in the other place. So we will be talking about derivatives with respect to proper time. Why? Because that is more convenient to deal with in relativity. And whenever there is a derivative with proper time, you will switch over to the normal quantities by using this relation, right? That's where the factor of gamma plays a big role. So this is a convenient, a very useful relation to go from one to the other. So we are talking about velocity here. So let's immediately write it as, this is, I can use chain rule. dt and dx alpha over dx. dt over ds is gamma over c.
I think you meant dx over alpha by dt. Is it?
Yes, correct. So this is t. My bad. Thank you. All right. So I use the chain rule for the course. Yeah. Sorry about that. And then write it explicitly. First of all, this is dt by ds is gamma over c, and dx alpha over dt. Let me write that. X alpha is ct, right? So what we are saying is this is d by dt of c times t, and the other one is dx by dt. Correct. The first derivative is trivial. It is the derivative of time with respect to time itself, the time, the usual time that any observer measures. So that's 1 or c remaining there, but then when we bring out the factor in, that c cancels out. So what we have here is I want to change my definition a little here. Sorry, I should have taken careful. We want to define what is a 4 velocity. And the way I have defined it on the right-hand side as derivative with respect to proper time, that is actually a dimensionless quantity, right? That's a distance on the numerator, distance in the denominator, that's dimensionless. So it's good to have dimensions of 4 velocity as velocity itself. So I'll multiply by a c here. Okay, this is a definition. So at the definition level itself, I will have a C there. So that introduces a C here. And that introduces a C here. So then C cancels out. When I take the derivative, C remains. So what we are left out with is says gamma times C, and here C cancels out. That's nothing but velocity, the usual classical velocity, if you want to know, or the tree velocity. Typically, you say that's the tree velocity, but it is multiplied with gamma. Right? So that's velocity v. And don't confuse, v is actually dx by dt, the standard, whatever we usually think of velocity as the rate of change of position with respect to time. That's your full velocity, like the zero component or the components. Remember, whenever we talk about a 4 vector, it's the vector components that are important. This will transform. Different observers will measure this differently. This will be different, this will be different. But the length of this 4 vector, by length, we mean the square of this and subtract from that. In the Lorentz sense, the length of this will remain the same for every observer. So that's the definition of 4 velocity. So that's what we want to keep in mind. Velocity still sits in there, but it's all scaled with a gamma. That's the new feature in there. Any questions in this? Yeah. Okay. Let me copy this down in here, and so that we can use that code. So this is gamma over C. So that's gamma over like gamma. That's an identity we have, which we'll use again and again. Okay. While we have, and the next will be acceleration, right? Once we have 4 velocity, we will define 4 acceleration and then the force. But before we proceed on, let's do some simple checks here. We said once you have a 4 vector, it has some properties that it is either time-like or space-like, or it could be even light-like, right? Remember the diagram we had. If you, so if this was time and if this was space, for all quantities here, the vector Ct is greater than x, let's say x squared, and here Ct, yeah, that's correct. Ct is less than x in this region. So these are space-like regions, or shaded regions, and the other one is time-like. And right on the edge sits the light-like quantity, because light, whenever you think of light, that is actually along this line. Familiar points? Okay, so there's time-like. So this is time-like. This is space-like, and that's light, right on the boundary. Is that clear, familiar? Okay. And every vector belongs is either time-like or space-like or light-like, always like that. Any vector in a space has to belong to any one of this, and we can ask velocity, what is it like? Like, is it a time-like vector? Is it a space-like vector, or is it a light-like vector? And the condition is, if you have a 4 vector A alpha, right? If A alpha times A alpha, so that is, you multiply it with the subscript of underneath that, and that is the magnitude of that vector. If this is less than 0, this is time-like. If it is greater than 0, it is space-like. And if it is equal to 0, that's like. Okay, that's your definition of time-like, space-like, or light-like. And in a graph, that looks like this. Okay, so let's immediately see what for velocity is like. So u alpha is equal to gamma times c and gamma times velocity. So it's scaled quantity with the factor gamma. Remember, gamma is always greater than 1. That's also okay. What is u downstairs alpha? Whenever you go from upstairs to downstairs or contravariant to covariant, it's only the time part that you have to switch. So it's C and gamma. That's all you have to worry about. And what is u alpha? Alpha, that will be the length of this vector. Length of this vector, not in the usual three-dimensional sense. This is the length in the Lorentz sense, where the time part comes out with a negative sign. So this is the same as u0 plus vector u after the vector u. So that's a summation index, summation notation, right? 0, 0, 1, 1, 2, 2, 3, 3. So that's a scalar product. But u0 is positive, 1 is negative, so that's where the negative sign comes in. So that's minus c squared times gamma squared. That's your multiplying these two quantities, that you see the negative sign, and plus gamma squared v squared, right? V dotted with v, that's v squared. Okay. That gives you, let's take out the minus c squared out. Gamma also can come out. So we have 1 minus v squared over c squared. One minus v square over c square is 1 minus beta square. 1 minus beta square in terms of gamma square is actually 1. Remember, did I define my gammas and betas? I think it was on the other side. So this is actually 1 over gamma square. This is exactly minus c square. These two cancel out exactly. Right? So that's minus c square, and then you ask, oh, that's a negative quantity because c is positive. So what is this? Is it a time-like vector? Is it a space-like vector? Or is it a light-like vector? So velocity is time-like. For velocity is time-like. Okay. What that means is that so what does a time-like vector mean? So if you have u of alpha, so u of alpha is minus gamma times c, gamma times v, right? A time-like vector means that you can always choose a frame. Now notice there are lots of frames possible. So there is some particle moving. If you, one easiest frame is that you sit on the particle itself. That's called the rest frame, right? Because relative to that frame, the particle is having 0 velocity. Or you could move with respect to that particle with constant speed. and there are a bunch of them. There is infinite such frames. You could go with speed of light, you could go very slow, you could go in opposite direction, you can go perpendicular directions. There are a lot of frames, but what a time-like vector means that is that exists a frame, so there exists a frame, so there exists a frame in which, so just to differentiate it from this particular U, I'll call it U bar. That's in a different frame, whatever this quantity is, there exists a frame U bar in which it is purely time-like. Right? So that's gamma, and let me call this gamma bar, so that it's not no more the same velocity that you will measure in that frame, times c, and this whole thing is 0. That's what it means to say it's a time-like vector. There exists a frame in which the spatial coordinates goes to 0. There surely exists a frame in which it is purely time-like. So now it's called a purely time-like. Which frame will take you from here to there? So suppose there is a particle moving around, and which frame is it where it is purely time-like?
Another frame of the particle.
Frame of the particle itself, right? You sit on the particle, velocity v goes to 0, right? This will go to 0, and you immediately get 0 here. And if that is 0, this will be 1 over 1, so that's c, right? So, so the forward velocity here, so in this case, is actually it's not even gamma, so this is actually c. So actually, I should say that this is always, if you are in that frame, it will be just c, right? Because gamma becomes 1 in that case, because its magnitude has to be equal to minus c squared. Right? So in the rest frame of the particle that is moving, its velocity is 0, and its fourth component is actually the speed of light itself. Okay, so that's the essence of speed of light. If you want, speed of light is the fourth component of the velocity. Whatever that means, physically, it is only the fourth component. That's all. That doesn't mean that it's actually moving anywhere. So that's just a quantity that connects with itself, so that the length of the vector always comes out to be the speed of light. Okay. Any questions on that? Okay, same thing goes for a space-like quantity also. If there is a space-like vector, there exists a frame in which it is purely space-like. That means all the time-like components can go to 0. And that has implications which we'll talk about later. Acceleration will come out to be a space-like quantity. So we'll talk about that later. So this, I don't know how to do. So this is, and that there exists a frame in which it is this quantity. Okay, so that's your for velocity. Let's define one more quantity. Let's say for momentum. Okay. For momentum is going to be very straightforward. It is going to be P alpha. Again, P0 and vector P comes in. But this is simply going to be, we define our usual momentum as mass times velocity. So we introduce M times alpha. So that's going to be the definition. But we should be a little careful. This M here is the rest mass of the particle. Okay. I will never introduce any other mass. It is going to be just the mass M. This is the mass of it. In every frame, it is the same. So it is called the rest mass. But usually, at a popular level, sometimes you have what is called a moving mass, in the sense a mass that changes from one frame to the other. But we will never talk about this. This is a fundamental property of a particle, irrespective of which frame you are in. It's always mass m. So it's called the rest mass of the particle. And the momentum will be defined as a mass times u alpha. And from this point on, things will change. Like, remember, velocity was the same. Right? Velocity is the same old velocity. Nothing has changed. But momentum will come out to be different. So that's going to be the new difference. Any questions at this stage? Okay. So that's all good. So these are all definitions at this point. This is where now we have to connect it with physics, right? That's where Einstein came in. He connected this with physical quantities, and so let me put this, write this again. The alpha is mass times u alpha, and that's equal to, if I were to explicitly write this, that is m times c times gamma, right? So that is gamma. How should I write this? Let me say this is c, and that is gamma, right? Let me actually one more. Let's the second one is m times v times gamma. Right. That's your. So notice the momentum, the spatial momentum is no more mass times velocity. Okay. Spatial momentum p, so this will be your p, right? So p is mass times velocity divided by 1 minus v squared over c squared. Right. That's your change, in fact. Right. And let me also do a small manipulation here. I'll multiply by a c here and divide by a c there. That's perfectly. That's your momentum. But now Einstein came and said that this is okay, but this is where physics comes in. You identify this as, so this is the connection. So this to this is the postulate, or Einstein's connection. So this is the physics, if you want. Right, this is the connection here, that you define the 0th component of momentum as energy. Okay. But the kinetic energy here, there is only one particle moving, there is no gravity, or there is no other force coming into picture. This is a free particle, right? Think of elementary physics. At this stage, we have no forces or anything. We are just defining velocity, acceleration, momentum, so on. So there is no nothing else coming in. So this is the kinetic energy, if you want. Right? That's your 0th component, and this is your momentum P. So that's the connection. This had to be postulated in a sense, and in this way, P, the free momentum, is no more mass times velocity. That's what I wrote just now. So that's mv times 1 minus v squared over c squared. The momentum is no more the same. That's a change in the definitions. And energy is equal to mc squared over there's a gamma out there, right? So, so that's 1 minus E squared over C squared. So if you want, you can, it's convenient to write things in terms of gamma. So it's gamma, and that's MC squared times gamma. 420. Okay, so that's your new definitions. Any questions at this stage as far as definitions go? Definitions. And now, before we proceed, there is one thing we can do immediately, and that is that since we did U alpha, one can immediately say, so let me just to save space here. So this was minus C squared. So that's minus C squared. Correct? So what can we do about P alpha? That seems to be an immediate calculation because this is mass times U alpha, and this is mass times U alpha with covariant coordinates, and that's m squared times U alpha. But U alpha, the length of the core vector is minus C squared. So that's minus m squared C squared. Right. Which means that this core quantity is again time-like, and it is always the mass, right? And that is a speed c coming in. What is P alpha? If I were to use this energy definition, P alpha is E over C times P. But the covariant quantity is minus E over C. So P alpha on one side, I said I calculated it as minus m squared C squared, but it's also equal to, if I were to multiply explicitly, that's minus E squared over C squared plus P dotted with P, that's E squared. Okay. And that's also equal to minus E squared C squared. If I were to rearrange this reads as energy squared is equal to P squared C squared, the momentum squared, plus m squared C raised to 4. This is the famous relation that this is the first time it was realized that mass contributes to the energy of the particle. So this is a free particle that's moving simply because it has a mass, it has an energy associated with it. And this is the idea of an atomic bomb, that it has, of course, momentum contributes to kinetic energy, but mass also contributes to that. And if you were to change mass, which is what happens in radioactivity, if you were to change mass, this energy changes. Of course, if P is equal to 0, right, if the velocity was equal to 0, E is equal to mc squared. But often, in the popular manner, this is defined to be the effective mass of the particle. So that's what usually they do. But I will never introduce that. M is the rest mass of the particle itself, and that's the That's Einstein's energy momentum relation. So now energy and momentum usually is half mv square, right? Half p square over 2m, but now there is a mass also in that. At this stage, one should also ask the question, how does it connect with your elementary physics? Like in elementary physics, energy, kinetic energy is actually p square over 2m. How does it connect with it? But that's usually straightforward. You just do a Taylor expansion. Let's convince ourselves of that, and then we will go to acceleration. Any questions here? Right. Okay. So in non-relativistic physics, so non-relativistic physics, we have energy and momentum to be given by p squared over 2m, which is the same as p is mass times velocity, so that's half mv squared. Okay, that's our relation. And one would think that in what sense is this connected to E is equal to p squared, c squared plus m squared, or c squared. So let's so relativistic scenario. We have energy is equal to, or energy squared, so energy would be equal to p squared, c squared plus m squared c raised to 4. And what sense is this the same as that? So let's expand this out. What was P? P was mv gamma, right? So let's write that down. So this is m squared, v squared, and then there is c squared divided by the squared quantity. So that's 1 minus v squared over c squared, and plus square c raised to 4, and so here I should be careful what I'm writing. So notice I used p here. P in this equation means, so it's necessary that we clarify this. So P here means m v space. So P in the second equation means m v times gamma, and P is in the first equation simply means mass times velocity, right? So let me change that notation a little bit. So let me call this P classical, right? PC. Just to clarify that that's not the same anymore. This is the actual momentum, which is a correct momentum, but the classical momentum or the non-relativistic momentum is simply mv. So that's PC then here, right? So that's PC squared in that, so that that we clearly see. So let's so this is equal to PC squared, and then c gets confused with speed of light, so let's change that. Not good. C is speed of light. How about nr, right? So it's a standard thing. So nr, non-relative. Okay. Non-relativistic momentum, and that's non-relativistic momentum square, c square, and 1 minus, that is again v here, it's a good idea to multiply by an m square there, divide by m there. So this is m square v square. So that's p square and r. But then I divide it by 2 masses. So that's m square c square. Plus m square c. And the question, you look at this and you say, oh, in what sense does this become that, correct? I mean, when does this become that? And the idea is that, remember, for small velocities, right? For small velocities, you can actually neglect this piece. So let's see what we get. So we can, so let v be very much smaller than c. In that case, we have v squared, so this can be neglected, right? So this is very much small compared to 1, and the energy then is equal to p squared so this is p nr square c square plus m square c raised to 4. This is not exact in the sense that I have already neglected, but I've neglected this quantity right here. But that's not your classical non-relativistic momentum still. So I have to do some more work. So what you do is you take the m squared c squared out. So the energy is equal to, let's take mc squared out of the bracket or out of the square root, and I have 1 plus p and r square c square and and c square c right? Yeah, so divided by m square c raised to 4. But we already are arguing that this is small compared to the non-relativistic case, because that's the same as v over c, right? That's the same idea. So this is equal to, so this is using expansion of square root, mc square times 1 plus half. Notice where the factor of half is coming from, because when you expand the square root, there is a factor of half, and that's p n square times c square over m square c raised to 4. And there are higher orders. So that's the same as mc square. Notice how the factors of c exactly cancel out, plus half p r squared over 2m. It is only this term that does not have c. Right? The first term has c, next terms will have c in it. This will be order b squared over c squared. That will be higher orders in there. And notice now what is the classical kinetic energy is this. So this is a non-relativistic kinetic energy. And the idea is also that there is energy associated with this, but this is so large compared to this non-relativistic term that we can keep it as a constant. So energy is always talked in terms of a constant. So this almost doesn't exist. So as far as change in energy goes, all the energy is coming from the velocity part of it, and nothing is coming from the mass associated with it. And that's the non-relativistic scenario, where energy, there is mass in there, but we don't talk about it. Change in energy is completely coming from the velocity part of it. So that's the connection between the momentum and energy in relativistic and non-relativistic scenario. Any questions here? You should have seen these things before also, I guess. Right? Okay, so that's all good. So now we have a for position, for velocity, and for momentum, and there's a connection between E and C also. So just a simple summary here. So we have X alpha is C times T times position X. U alpha, which is defined to be the derivative with respect to proper time. This is gamma times C and gamma times velocity. Momentum, for momentum is defined as m times u alpha, and the connection here is that we also introduce energy, right? So this is energy, or how do you say this? So this is mc gamma times mv gamma, and that's also E over C and P. So that's a summary of whatever we have talked about, and there are conclusions saying that the length of this vector is time-like minus c squared. Length of this vector is mass. So length of the momentum is mass, if you want. Length of the velocity, for velocity, is speed of light. Right. So that's another way of looking at it. And by length, I mean the invariant quantity. If you were to measure the length of momentum, so you will get the mass. In every coordinate system, mass remains the same. So it's mass that has everything in it. Or another way of looking at it is that if you increase the energy, momentum comes down, right? Somehow, or both have to increase. I think better way to say it is that both have to increase in such a way that the difference in the squares has to be kept the same. So that's the way one looks at relativity. So that's all good, but we have to go further, right? This is only velocity. If we have to talk about force, we have to talk about acceleration before that. So let's talk about acceleration, and for that purpose, let's define what is for acceleration. That's a alpha, and that's equal to, we have to define this. So we will define this as all the derivatives will with respect to proper time, right? Try to do this. So let's be s. That's going to be our for acceleration. Whenever we have derivative with proper time, we immediately convert it to derivative with normal time, the coordinate time if you want. S and the alpha over same idea as earlier, but I did not keep it on the board. dt by ds was gamma over c, correct? Yeah, gamma over c. du alpha over dt, that's the same as derivative of with respect to time of gamma times c, that was the zeroth component of velocity, and d by dt of gamma times the velocity. That's clear? Yeah. C can come out, so we have this is equal to, I take the C in, let me say this is, let me keep the gamma outside. This is d gamma over dt. You calculate that, derivative of the factor gamma with respect to time, c cancels out, and here there are two terms, right? I can either hit on gamma or on velocity, and when it hits on velocity, that's our old acceleration. This is first of all, there is a c. I will put it all the way with velocity. So this is the gamma over dt times velocity over c, which let me call it beta. Or I can hit the velocity itself plus and that will be defined as acceleration. So this is the old standard classical acceleration. So acceleration A here is dv by dt. The same Newtonian acceleration. That seems like it's a little tedious calculation. Here, what is gamma, d gamma by t dt, right? That's what we expect. So it doesn't seem to be having a very clear insight for picture here. So let's go ahead and to that end calculate the derivative of gamma with respect to time. So let's okay, so but instead of calculating gamma the explicit way, so let's use a trick. We already showed that u alpha times u alpha is equal to minus c squared. Right? We already showed that. That c means that I can take a derivative of this equation. The derivative of this equation will be du alpha over ds. By derivative, I meant derivative with respect to the proper time times u alpha plus u alpha times contravariant is equal to 0 because speed of light doesn't change with whether proper time or any time. Speed of light. These two are exactly the same relation, right? It doesn't matter whether I write up step or down step. This is acceleration. Right? So this is a alpha, u alpha plus u alpha times a alpha equal to 0. These two are exactly the same. So that's 2 times u alpha times a alpha is equal to 0. So the factor of 2 cannot be 0. So you have can we say anything about what the acceleration, for acceleration is from this relation. Remember, whenever you have two vectors in 3 dimensions, if that dot product is 0, what can you say about the vectors? If the dot product between two vectors is 0, what can you say about the vectors themselves?
Perpendicular.
Perpendicular, right? So this is an orthogonality relation in 4 vectors now, but what does it mean? How do you talk about that? So first of all, we know that U alpha is time-like, right? So U alpha is time-like. So you go to the frame. So you go to the frame in which it is purely time-like, and that will be U of 0, which we said is C, and 0. Right? So it is always possible to go to a frame in which that's purely time-like. In that particular frame, what happens to acceleration? In that particular frame, acceleration, the covariant part of this, it'll be some A0 here. So there is some A bar 0, and there is a factor A, like a vector A. That's not vector A, let me call it AI, A bar. The 3 components of the acceleration, whatever is down there, right? That's which will be exactly your actual acceleration. But that's good. But what about the squared quantity here? What we are saying here is that this times this is 0, and that will be 0 in any frame. So U bar, U alpha, A alpha being a Lorentz invariant, that's going to be equal to U bar alpha times A bar alpha. But we know what that quantity is. That's getting contribution only from these 2 terms. C times, and there is a oh, there was a minus sign here, right? So minus a naught downstep.
What does the bar indicate?
Bar means this is a person. Okay, this is your 4 velocity in a frame. I go to another frame. I call it X prime, for example. Usually we go from one frame to the other. We say the coordinates have changed in rotation, so X prime. But this is a very special prime coordinate in which the velocity is purely time-like. So a frame in which velocity is purely time-like. In that acceleration, we don't know what happens. So in that, whatever it changes to, that's what it is. But now, this is in that prime frame, this is minus C times A naught. And in fact, we can go ahead and see what happens to this quantity. Can we read that out here? That's A naught, so that's gamma times derivative of gamma with respect to time. So what was I trying to say? Oh, yes. So what I was trying to say here is, yeah. So this is a logical conclusion I'm trying to make. This. So U alpha, we are in a frame in which it is purely time-like. In that frame, acceleration has both time and position. the product of this quantity is minus C times A alpha, right? Minus C times A naught, right? Because that's 0 and a 0. But this is equal to 0 already, we know, so that's equal to 0. So what can you say about A naught now? This is A bar, right? Sorry, not vector. Speed of light times A naught is equal to 0. So what can you say about A naught in that particular frame? It has to be 0. Right? So this implies that A naught bar is equal to 0. Okay, so in that same frame in which speed of light was purely time-like, actually acceleration is purely space-like. So this implies that A alpha is space-like. Okay, one can also calculate this. You can go ahead and, since we know the acceleration, that you can multiply A alpha and A alpha, and that will come out to be a positive quantity. That's much more tedious. This is a simple logical argument gives you that A alpha is space-like. Okay, so but can we learn something more about it? Notice if we are to proceed, we want to calculate this derivative. So let's go ahead and calculate this U alpha A alpha. So we have this relation. This is equal to 0. Right? Can we learn something about this? So we are 2 minutes past our usual time. Just do you have a class? Angela? Do you have anything in the next few minutes?
No,
No, I'm good.
More maybe? Maybe I can do this in 5 minutes. If not, I'll just give up and we'll do it next time. Since we are here, it's better to finish this up. This is the same as saying this is U0. Let me write that down here. Oh, we have it here, right? U alpha and A alpha. So this is U0, A0, U0, maybe I should. So U alpha is equal to gamma times C, gamma times velocity, and A alpha is equal to, I have to switch the sign there, so that's minus gamma times d gamma over dt, and you have space-time remains the same. Theta of gamma squared and acceleration, and then the gamma here also. Then you just expanded things out there. This times this is 0, so I have to take the product of this. So minus gamma squared times C times d gamma by dt, by these two, and plus this multiplied all through. So that's plus gamma squared. V times this is gamma by dt. V is nothing but beta times C. So this is beta squared times C. That's this quantity multiplied. And the third piece is gamma cube times beta times acceleration, and again speed of light C in there. And all this is equal to 0. this gives us what we were looking for, d gamma by dt. The c cancels out. So let me write this down clearly. So that's gamma squared d gamma by dt. C cancels out, and I have 1 minus beta squared. All this goes onto the right hand side, and that's equal to gamma cubed times beta divided with acceleration. 1 minus beta squared cancels with gamma squared. So I have this relation that the time derivative of this gamma, which is a coefficient that decides how fast your frame is going, that's beta divided with A times gamma cubed. And this is correct. This doesn't, there seems to be some problem with a dimension, right? Did I miss a C somewhere? Oh. Yeah, I'm missing a C somewhere. Correct? Dimensionally. And that is because right here itself is to that's velocity 1 over time, and this should have a C. So there is a C here, right? So because C, this has to come all the way here. So there's a C here. C there, so I introduce this C, and that changes C, and that is C here, and that's a C. That's okay. So now C cancels one of the velocity in this. So that's a relation we will use in the next class. It looks at this point not very insightful, but the moment you put that in, this will show up in scenarios where velocity is perpendicular to acceleration or velocity is parallel to acceleration. There will be different types of relations you will have. Next time we will come and define force or acceleration itself when velocity is perpendicular to acceleration and velocity is parallel to acceleration. Different scenarios show up, and it will help us calculate what happens to a charge in an electric field versus magnetic field. And we'll do this and talk about Newton's second law. And from that point, we can go into electrodynamics of this scenario. Any questions? Okay. So this seems to be okay, right, Justin?
Yeah, this is fine.
Yeah. Okay. Okay. Good. Okay. Take care, guys. Justin, I did get your email, and I'll.
Oh, for the extra credit or the recommender thing?
Both. I got a letter for your extra credit and another letter also.
Okay, excellent.
Okay, good. Okay, take care.
You too. See you next time.
Mm-hmm.